Hi everyone. Today I'm going to talk about section 2.8, the derivative as a function. Um, so firstly, let's talk about the definition of derivative functions. Um, Let me use my wait this highlight. Okay. So for any function fx, we define the derivative function f derivative of x by f derivative of x equal to the instantaneous rate of change of f at x, and also equal to the formula as we learned in the previous section. Limit of fx plus h minus fx over h for h go to 0. And we say that f is differentiable at x. Okay, so down here in example 33, we have two graphs. Let me move up a little bit. Right. One graph is for f. One graph is for f, the blue one. And the other graph is for f derivative of x. So here's fx, and here's the f derivative of x. Okay, so from here, we're gonna try to figure out what happened when the f derivative of x equals 0, and when the derivative of x is so when derivative of x equal to 0, when derivative of x is greater than 0, and when derivative of x is less than 0. So so you can see at a in here, a prime in here, right? At a prime and b prime and c prime here, they are the f derivative of x equals 0 here, right? So that's at that point, what happened with f of x? Okay, so from here, you go back to the f of x and see in the graph of x, we have the graph have like a local minimum, right? It's go from it decreasing, and then until this a prime is go increasing, right? So it was decreasing, and then until this point it stop here, and then it's go up later, right? So so that means what? That means at point A here, right? At point A here, the the slope was what is tangent line at this point? It was a horizontal line, right? And the slope for this horizontal line has to be equal to 0. You should learn in algebra that for any horizontal line, right? So let me load that. Horizontal line has slope equal to 0, right? So in here I have the tangent at point A was a horizontal line. So the slope at that point has to equal 0, right? So also when it's go up to B, also you see that's the f prime of x in here is 0, which is the slope of the tangent line, right? So go back to tangent line here. It also is horizontal line, right? So you can see that any when you see the graph that have a horizontal tangent line, then the derivative of x gonna be equal to 0. So tangent line. So I'm gonna have for the horizontal line, tangent line, it's gonna be make the f derivative of x equals 0. So let's move down here. So if f derivative of x equals 0 on an interval, then fx is a constant on that interval. So let's me, this one is this fx is stand for the tangent line, okay? Let me come back with this one, okay? So if tangent line is horizontal, then we have f derivative of x equal to 0, right? So also at point C, I have a horizontal line over here, tangent line. So the slope or the f derivative of x has to be equal to 0. So the graph of f derivative of x cross the axis f at C, okay, at C prime. So now what about let me use other color. What about when f derivative of x less than 0, right? So let's see over here. F derivative of x is less than 0. Just take a look at the part that f derivative of x less than 0, right? See that? Only this part, right? From negative infinity to a, right? And to a prime, right? See that? That's gonna make the f derivative of x less than 0. So let's take a look at the graph from negative infinity to a of the fx, of the graph of the x. So you see that what happened with the f of x over here? It's just going down. We mean what? It's decreasing, right? See, decreasing. The graph is just decreasing. Then it make the tangent line also decreasing. Okay. So fx decreasing make tangent line decreasing, and that make f derivative of x less than 0. Okay. So at that point, at that part, the slope of the tangent line is decreased. That means, the slope of tangent line has to be negative because the tangent line going down at that time, right? Okay. So similarly, from B to C, right? You see that it's just decreasing, right? So for the fx, you don't really care about is that positive or negative. It's just you just care about it decreasing or increasing. That's gonna help you to determine the negative or positive of the f dv of x. Okay, so now so now let me check on the part that have increasing or that have positive f, that have f dv of x positive. Over here is one part and this one also. So from a prime to b prime, f dv of x is positive. And from c prime to positive infinity, you have f dv of x positive. So look back at the fx graph. You see that it's increasing from a to b, right? See that? Increasing from a to b. And then from c to positive infinity, it just keep going up. It's just increasing. See that? Right? Increasing. So I will say, move up a little bit. Fx increasing make the tangent line increasing. So then the slope or f dv of x of the tangent will be greater than 0. Okay. So important message: every point at x on the graph, every point at x on the graph of the derivative function represent the slope of the tangent line to the point x of the original function. Okay. Now let's move to the question over here. What does f dv of x say about the graph of fx? Okay, so first, if f dv of x greater than 0 on an interval, then fx is increasing on that interval. See, that's what I just mentioned above, right? And then secondly, if f dv of x less than 0 on an interval, then fx is decreasing on that interval. Okay, so let's go back, right? Right. If f dv of x over here is positive, then on an interval from a to b, right? Then the f of x is increasing from a to b, right? See that? Similarly, if f dv of x is negative from net infinity to a prime, then the fx is decreasing from net infinity to the a, right? See that? So let's move down. And lastly, if f dv of x equals to 0 on an interval, then fx is constant on the interval. Actually, in here, if you see at b prime f dv of x equal to 0, right? Then fx now is a tangent line, the horizontal tangent line. So that means it's just like a constant number. Okay, so here constant. It's A here. It's A here. Right. Now the horizontal line, and here it's just fx equal to A. Right. Okay. So let's move down. All right. In example 34 here, if f of x is equal to c, which is a constant, what is f of x? So here is fx equal to c. Let me, all right. So so I'm gonna say this is like the 10 horizontal tangent line, right? If x equals c, right? You can see that it is clearly is a horizontal tangent line, and you can have a slope gonna be equal to what? 0. So so you can right away has the f of x had to be equal to 0 everywhere. Say everywhere. Everywhere. So that means the f derivative of x had to be exactly the x-axis. Here is f derivative of x equal which also going to be equal 0. Which also going to be the y equal 0. Okay, on the x-axis. Okay. What about example 35? If x equal to mx plus b linear. So you see in here is a linear, right? And this linear, look when you look at this linear, it's just increasing. See that? I mean, yeah, it's the slope in here is should be positive, right? Should be positive. Seeing the fx is increasing line, okay, and also it's a linear. So then f of x gonna be just the slope of this tangent line. Yes, just the slope of this tangent line. So so I'm gonna say slope equal to m everywhere. Okay. So since it's a slope equal to m everywhere, that means what? That means I have the function of f of x is going to be equal to m everywhere, right? So, and also remember that since this is an increasing line, then the slope has to be greater than 0, right? So then you have the f derivative of x has to be a horizontal line at y equal to m, and m in here should be greater than 0. So horizontal line. Okay. Okay. So let's move down here. I have f x equal to a squared x plus b of x plus c, which is a parabola, right? And we're gonna discuss about what is f of x. This could be a little bit harder than the one before. You should try to think about a question over here as is the slope larger at x equal to 6 or at x equal to 3. So let's take a look at 6. 6 was here, right? You have a slope for the tangent line like this, right? For as x equal to 3, p is around here. So who is his guy? So tangent line look like this. So you can see that as x get larger, right? Then it look like the line is steeper, right? So the slope actually gonna get bigger if you have larger x. So I'm gonna say as x get larger, let's see, larger, the slope will get larger or steeper. Sorry, I should say that steeper, because later on I also want to check. So then slope has a larger number. Okay. What about in negative direction? This is from here, from x equal to 2, right? You have horizontal line was at x equal to 2. Let me use the color. Oops. Right. But yeah, so what I mean, these are gonna be positive slope. This side gonna be negative slope. Okay. So if you have like in negative direction, the slope is kind of like the more negative. So the more negative you're gonna have, the more negative you're gonna have, the more steeper, but in the negative way. See that? See that? So so more as x get larger negative, then m get steeper with m get larger negative. Okay. or it's going to be like s x go to positive negative infinity, negative infinity. Okay, so for the case that what is f derivative x function, let me see. You should have, like, you should know that at x equal to 2, at x equal to 2, the slope going to be equal to 0, right? And x equal to 2, slope equals 0. So let's say here's 1, here's 2. So the slope, or the f equal x, f equal x equal to 0. It should be go through this point, right? And you since you know that's the more negative, the more negative of the x of in the fx, you're gonna see that the graph is decreasing, right? After 2, it's a graph is decreasing from the negative infinity, and also it's still gonna get like a like I say over here, m gonna be get larger negative. So like after 2, like like before 2, it was a negative number. Our value just become very, very negative. So it's really yeah, and also after 2, it's become like positive because the graph is just increasing. See that for the fx original one, it's just increasing after 2, and then before 2, it's decreasing. So then the f of x, derivative of x has to be positive in this side after 2, and then negative in this side after 2, before 2. So I can draw a line, go to 2, not correct, go to 2 over here, right? Not really nice. Let me try one more time. Okay. So, oops. All right. So the slope of, I mean, the line should be I mean the f derivative of x has to be a line, a linear equation with a yeah, with a like negative before 2 and positive after 2. So that means the line here should be like increasing. The derivative has to be a decreasing line. I'm sorry, increasing line. Okay, so that's for example 36. Let me move down. Okay, why do we care about the derivative? Okay. Suppose the sales of an item as function of price look like this graph. Okay, so the graph here, this is the sales Okay, cell function. Or function of price. Okay. Sales suppose sale of function as a function of price. Let's say price. Okay. Wouldn't you want to know what price make the sale increasing? Okay. Sometimes it's not easy to get from the graph F to get exactly. We use a derivative and see exactly where the function is positive. Okay. So we actually need to know like where where is exactly we know that's from it look like from here to here it is increasing right. The price makes itself increase. Okay, but we want to. You can estimate it is from 2 to 8, but how can we know? So we want to answer the question as where exactly is this region, right? Where exactly is this region? We want uh, to to use the derivative to find exactly this region. Okay, so let's move up. And yes, I would like to let you guys to try on exercise 27. We're gonna try to match the graph of each function is a to d with the graph of its derivative in 1 to 4, right? So try to like connect, like for example, what is the of the a of the graph a here is you should look for one of these in here, right? And remember that like when you want to look for the derivative of the original function. So let's say for the original function, you just care about when it's decreasing and when it's increasing. So say from here to here is decreasing. You're gonna looking for the graph that here from negative infinity to this point is negative. So something like that. So you're gonna look for something that's just negative. So it look like this one have negative, but from negative infinity to 0. So it's not this one. Okay, something like that, right? So I will let you guys to try on this one and see what happens. Okay, so let's move to the next problem. Example 37. So if f of x equal to square root of x, we're gonna find the derivative of f state and then state the domain of f derivative. Okay, so let's see. Okay. Firstly, we have this is a graph of fx. It was square root of x. Okay. Now we try to find the derivative of f. Okay. So remember that if you have know that the derivative of fx will be defined by the formula limit of fx plus h minus fx divided by h for h go to 0, right? So let's we do a sidewalk. Okay, let we have a sidewalk here. Sidewalk. You have if x plus h was what? Square root of x, now change to be x plus h. Good. So then now you can just plug into this function and see what happens. So I have x plus h is going to be equal to square root of x plus h minus fx now was given by square root of x divided, oh, I forgot the limit. Okay, let me, okay, all right. So now what should you do for the next step? You cannot direct substitute, right? You cannot factor for the top. What should you do? You must think about the top right now having a subtraction between square root. So you have to think about, can you use the different between different square formula for this case, and you want to multiply with the conjugate of this, right? So so you're going to multiply with conjugate it. You need to multiply by, use as a color. So you need to multiply by square root of x plus h plus square root of x, right, for the top. And you're going to also do the same at the bottom, h square root of x. So now you actually can have the limits of I should have a parenthesis here so I don't forget. The limit of square root of x plus h everything square minus square root of x square and then divided by h. H multiplied by square root of x plus h plus square root of x. For the bottom, don't ever think about distribution because later on you want to eliminate this h so you can direct substitute, right? So keep it factor. Okay, for the top, you're gonna try to simplify it and see what happened, right? So you have that's gonna be equal to the limit of x plus h. Okay, now the square root gone because of square, right? Minus the x, and then divided by h, multiplied by x square root of x plus h plus square root of x. So now you can see that there is something to cancel on the top, which is x and negative x. And now you're actually going to have h divided by h times with square root of x plus h plus square root of x. So you can easily pass you can easily cancel the top and bottom with the common factor h. And remember that you still have number 1 on the top here, and don't forget the limit, right? So now you're gonna have limits. No, you just, oh yes, you're gonna have limits of 1 divided by square root of x plus h plus square root of x for h go to 0. Okay, time 2 direct of 2, right? Direct of 2, you have 1 over square root of x plus 0 plus square root of x. And that's going to give you 1 over square root of x plus square root of x is 2 square root of x. And this should be the FDV of x, which is this one, B. And you can see that if you try to graph it on Desmos, you're gonna have the graph of the FDV of x is here, and you see from and you see that the graph go up to positive infinity when x go closer to 0, right? So what happened with that? Because x in here is just go down and down to and stop at 0, right? And at this point, the graph um, the graph just stop at 0 and never go down more. So the tangent line is very steep, right? Very steep at this. Very steep at this point. So that's the reason why you have the slope or the FDV of x function go to positive infinity when x approach to 0, right? You see that? Okay. And similarly, later on the graph, it's just, even though it's keep going up, but like a very flat, right? It becomes flat, turn flat, right? And so what does that mean? That mean the f of x, FDV of x is always positive, but later on it just become closer and closer to 0, right? Closer to 0, right? Let's just keep going. Okay. And I forgot domain, right? So I may have to this, right? So domain of f derivative of x. You can see that domain is all value of x. So you can see that the value of x is from 0 but not include 0, right? To the infinity. You see that the graph is just from 0 to the positive infinity for the value of x, right? So so then the domain will be from 0 to positive infinity. Okay. Let's move to the example 38. Right. If f of x equal to x cubed minus x, we're gonna find a formula for f of x. Okay. All right. So for this problem, we still gonna using f of x equal to the limit of f x plus h minus fx divided by h for h approach to 0. Okay, so maybe I need a sidewalk. I'm gonna put a sidewalk down here. Right. I have f x plus h. Where is that gonna be? I have a x plus h to power 3, right? Minus x now change to become x plus h. Okay. So I can extend it out. If you guys remember the special form for the cube for the power of 3 binomial, you can write away here x cubed plus 3xh plus 3x sorry 3x squared h and then 3xh squared and then plus s squared. Yeah, that is just for the x cube. If you forget it, you can just do the distribution, and finally you're gonna get like when you try to extend by using the distribution, you're gonna have the same thing here when you combine it. Okay, so now you will subtract for the x plus h. Actually, I can just do distribution for the parenthesis here with the negative. So you're gonna have minus x and minus h. So you will have what? X cubed plus 3x squared h plus 3x s squared and plus s squared minus x minus h. Okay, so that is just for x plus h. Now I will substitute in. So it's going to be equal to the limits of x cubed plus 3x squared minus 3x squared h plus 3x squared, and then plus h squared minus x minus h. Okay, and then you will have divided by no, you're gonna have minus fx, so x cubed minus x, and then divide by h. For h go to 0. Oh yes. Okay, so now let's open the parenthesis for the top. So it will be x cubed plus 3x squared h plus 3xs squared. Let me see. Plus h minus x minus h, right? And then minus for the x cubed plus for the x. So you can do what? You can cancel x here with x here. Oh, there is square over here, I forgot. No, not square, it's be cubed. Oh, I forgot. It's be cubed. Cube. Sorry. Cube. All right. And also you can cancel the x cube with x cube here. So now divided by h. For h, go to 0. Okay. So now you would try to have a factor at h on the top so that you can cancel the h. Okay, that's our strategies. Let me change the color. I'm gonna have limits of h equal to 0 for h. If I take h out, I have 3x squared. Is now gone, right? Plus 3x h plus h square, right? And minus 1. Maybe I change the color so you don't mess up with it. Okay. So now bottom going to be h, and you can just cancel it. And direct substitute, you will get 3 times 0 square plus 3 times x times 0 plus with 0 square minus 1. So the answer should be -1. Oh, wait. We still have x squared here. Okay. So you in simplified form you have 3x squared minus 1. Which gonna be the function f derivative of x. Okay. And similarly, the slope, the graph over here is the f derivative of x, and the one up here gonna be f of x. See, you can take a look at when it's negative, positive for the f derivative of x, and when it's increasing or decreasing of fx. Okay. So we have exercise to try for you is 28. Go ahead and do it. Then we're going to talk about the notation, some notation that you may need, and you're going to see in this calculus class. Firstly, you may encounter many different ways of expression the derivative, right? So let y equal to fx. Some common alternate notation for the derivative are y derivative also dy over dx, also like f derivative of x, or also going to be df over dx, and then d. Oh my goodness, sorry. D over dx multiplied with fx. Okay. Another one is like this one, but I would say like mostly you will see is from here to here, mostly, or you can include this one also. That's fine. But kind of never seen something like dfx and dx over there, right? And the definition, a function f is differentiable at a if attribute a exists. It is differentiable on a open interval or a to infinity or negative infinity to a or negative infinity and negative infinity. If it is differentiable at every number in interval. Okay. Yeah. So we're gonna have theorem 5. If f is differentiable at a, then f is continuous at a. Okay. We know that the converse of the theorem is false. What does that mean? Wait a second. Oh. Use this one. So there are functions that are continuous but not differentiable. Okay. So how can a function fail to be differentiable? Okay, cool. If you see the kink or corner, so over here is one of the reason with the corner. Any discontinuity, that's gonna make no differentiable for that. And then vertical tangent line. Vertical tangent line. Which is here, I think. Yeah. Vertical tangent line. And then here's the limits of any value of x put absolute value of any value of x is gonna be infinity. Okay, so the third case is discontinuity, right? And the last case is vertical tangent. Okay, all these four picture that will make the function fail to be differentiable. So you cannot take the real for those. And here is something another way thinks about it. So so look like it zoom in and get a line, right? Zoom in and get a line. Because it's like zoom in. Get a line. And then zoom in on corner. Oops. Okay, number 39. Where is function fx equal to x? Absolute value differentiable Okay. So so you can see that at here the function has like a corner. Okay, corner at 0. Right. So then so then at this point there's no the function is doesn't have differentiable for this point x equals 0. So so we can say as the value of x is differentiable everywhere except x equals 0. Okay, so only at that point. Other than that, everything else good. So we just gonna say that. Okay, so last example is a function f(x) equal to x squared minus 1 differentiable everywhere. So remember that for this is a rational function. Firstly, right? You right away can think about the bottom. What happened with the bottom? What happened with the domain, right? So so domain is can be real number, right? Domain x is real number except so real except so 1 x equal to 1 because when x equal to 1 that makes undefined. So so then you can have fx at x squared minus 1 can be changed at x minus 1 times x plus 1 and divided by x minus 1. So now you can cancel this and have like x plus 1. Okay. However, so this graph is look like the line, or just say is the line y equal to x plus 1 with a hole, right? With a hole x equal to 1, and then I can say so the function is not differentiable differentiable at x equal to 1. Okay, so this should be it, and I will see you next time on the other section.